Okay, we were talking about this pressure last time, so let's continue. So we learned that the pressure changes in the gravity direction, and we know that pressure increases when we move in the gravity direction. So if you look at by how much, by using this equation, delta P is rho GH. So if we have two positions, let's say number 1 and number 2, let's say this one is number 1, this one is number 2, and this is the gravity direction G, then the pressure difference between P1 and P2, we can calculate that by using delta P is rho GH. Between P1 and P2, we know P2 is greater than P1 because pressure increases in the gravity direction. So if you want to determine delta P, which is the difference in pressure, we need to use P2 minus P1 because P2 is greater than P1. If you calculate P1 minus P2 because P2 is greater than P1, if you calculate P1 minus P2, it's going to be a negative value, and this delta P, the difference in pressure, cannot be a negative value. So this should be P2 minus P1, not P1 minus P2, should be the same as density times gravity times h. H is the height between these two. Okay? So that's how we can determine pressure change between two locations. If you look at this figure, you can see on the left-hand side, each arrow means the length of arrow means the pressure. So you can see pressure increases in this direction. By how much? By delta P is rho GH. You can also see here pressure increases in the gravity direction. But if you look at the top surface, the length of the arrow is constant. That means pressure is constant. Imagine that that you are walking from here to the another building the on campus. You don't see a significant pressure changes because pressure only changes in the gravity direction. But if you go into the swimming pool in the sack, if you dive into the water and you go deeper, and then you feel that the pressure increases when you go deep because of this low pressure increases by this much. And if you look at the bottom of this rectangle, you can see the longer arrow, meaning is that the pressure at this point, at this surface, is greater than the pressure on top of this rectangle by how much? By delta P is rho GH. Okay, so the difference in pressure between this location and this location is going to be rho GH. Then let's look at this figure. First of all, you see this upside down triangle. This means the pressure at this surface, on this surface, is going to be the atmospheric pressure. So when you see this one, upside down triangle, that means the pressure at this point, P is P80N, the atmospheric pressure. And the standard atmospheric pressure is 180 N, is, by the way, 101.325 kilopascal. Okay? Then, can you determine the pressure value at point A if you know height h? Yes, you can. Then what is the pressure at this location? We can use the same equation. Delta P is rho GH. Okay, where? Oh, yes, kilopascal, yes. So in Pascal, it's going to be 101,325 Pascal. So it's going to be 101.325 kilopascal. because 1 Pascal is too small. We prefer using kilopascal. And you can use this delta P rho g h between point A and the surface. And how can we do that? Delta P is rho g h. What is delta P between PATM and PA? Between PATM and P at point A, we know PA is greater than PATM because pressure increases in the gravity direction. So if you want to determine delta P, we have to say PA minus PATM. You cannot say PATM minus PA because this one is greater than this one. If you calculate PATM minus PA, it's going to be a negative value, which is incorrect. Then density times gravity times h. So if you know height, h, and we know gravity, which is 9.8 meter per second square, and the density of water is 1,000 kilogram per cubic meters. So this one is 1,000 kilogram per cubic meters. It's going to be PATM, which is 101.325 kilopascal, and minus PA. So you can determine PA if you know H. Then what about if you want to determine the pressure at the bottom of the swimming pool in the set? What is the depth of the swimming pool in the set? Maybe approximately 1.5 meters. When you jump in, can you breathe? Right. You can touch the floor, right? Have you been there? Yes. Yeah, right. You can touch the floor, right? So let's say, that the height of the swimming pool is going to be, depth of the swimming pool is going to be approximately 1.5 meters. Should be correct. Then you can calculate the pressure at the bottom of the swimming pool by using this equation. Pretty simple. Then let's do that. What is 1,000 times 9.8 times 1.5? Use a calculator. 1,000 times 9.8 times 1.5. I get 14,700. So PA is, if you move this one to the right hand side, is 101.325 kilopascal plus 14,700. Then what is the unit of this one? Kilogram per cubic meters, meter per second square times meter. The unit is, we have cubic meters, meter, so it's going to be kilogram per meter second square. So what kind of unit is that? We have kilopascal here. So is it kilopascal? How do you know? By using dimensional homogeneity that we studied last week. What is dimensional homogeneity? If you don't remember, there are primary dimensions and secondary dimensions. There are only 4 primary dimensions that we study in in thermodynamics. They are meter, length, and mass, kilogram, and time, second, and temperature, Kelvin. So there are 4 of them. And any other, any secondary dimension, such as Pascal, is going to be a combination of primary dimensions. So you can divide any secondary dimensions into combination of primary dimensions. If you keep dividing, and you will only see these 4. So let's do that. You can do that. Let's talk about this Pascal. What is Pascal? This is the unit of pressure. Pressure is force times force divided by area, right? So what is the unit of force? Newton. What is the unit of area? Meter square. So Pascal is Newton. So Pascal is Newton force times area. Then, so that was the secondary dimension. We divide this secondary dimension into two, Newton and meter square. And are they primary dimensions? Meter is yes, but Newton is not. So we can divide this Newton into, the several primary dimensions. So what is Newton? The unit of force. Force is what? Mass times acceleration, right? So what is mass? Kilogram. What is acceleration? Meter per second square. And we have meter square in the denominator. Okay, 1 over meter square. So Pascal is what? Kilogram meter, we can cancel them out, divided by meter second square. If you look at this one, you can say the unit of this one is Pascal. So if you know how to convert between primary dimensions and secondary dimensions, you can check whether the units are right or wrong. So from this, we learned pressure at point A is going to be, oh, why are you using the lowercase? Pressure at point A is going to be 101.325 kilopascal plus, it's not 14,700 kilopascal, it is just Pascal. So this one is just Pascal. So if you convert into a kilopascal, it's going to be 14.7 kilopascal. So what is the pressure at the bottom? 16.025 kilopascal. So this is the pressure value at the bottom of the swimming pool in the set. So by using this one, delta P rho GH, you can calculate, you can determine the pressure value in any location on the Earth, as long as you know the density and height, because gravity G is always 9.8, right? Then going back to this point A, now we know pressure at point A. Can you determine the pressure at point B? If H is the same, yes. Then what is the relation between PA and PB? PA greater than PB or PB greater than PA? Yeah, they are equal. PA should be the same as PB because we have the same density, water, we have the same height, H. As long as rho GH are the same, pressures should be the same. So PA, PB, PC, D, E, F, G, they all equal. Make sense? So the same as, if you go to, the library in the first floor, you feel the same atmospheric pressure because same density of air, same gravity, same height. If you go to Midland, you feel the same atmospheric pressure, right? Same H, same G, same rho. But if you go to Denver, Colorado, you don't feel the same because they have a different H. But if you go to, let's say, New York or Florida, the near the sea level, like, the Mount Pleasant, we feel the same atmospheric pressure because of this one. Okay? Then let's look at this one. There's another point, H and I. They're at the same H from the surface. So pH, Pi, what is the relation? Are they the same? Equal? But if you look at here, they are a little darker than the surrounding. This one is mercury. So should pH be the same as Pi? No. Why is that? Because mercury is heavier than water. That means the density value of mercury is different, is greater than the density of water. So between pH and Pi, we know they are not equal. Then is pH greater than Pi or Pi greater than pH? pH should be greater than Pi because it's in mercury, which is heavier. So the pressure increase in mercury is greater than pressure increase in water. Think about this. When you go into the swimming pool only 1.5 meters deep in the swimming pool, you can see pressure increased from 101 to 116. But if you go to the second floor, or if you go to the basement, if there is, then do you feel that much pressure increase? No. Because water density is much, much greater than the density of air. So then what is the density of air? Just for your information. The water density is 1,000. What is the density of air? It depends on the temperature and the pressure of the location, but in general, approximately 1.2 kilogram per cubic meters. The density of air in atmospheric pressure at about room temperature, it is approximately 1.2 kilogram per cubic meters. So if you consider pressure change in air, this density value is too low, so we don't experience large variation in atmospheric pressure change because of the low density. That's why you can climb the Mountain Everest. But you cannot dive into the water only 20 meters. You cannot breathe because of the pressure increase is very significant. Okay. So that's everything about this slide. Then we studied last week, there are 3 different pressures: absolute pressure, gauge pressure, and atmospheric pressure. How they are related? PABS, absolute pressure, is P gauge pressure plus atmospheric pressure. So when I say there is a system, there's a gas tank, gas chamber, about this. And there's a pressure gauge. And when atmospheric pressure, ATM, is approximately 100 kilopascals, when this gauge shows the reading of this pressure gauge is 200 kilopascal, what is the absolute pressure of the gas inside this chamber? Because you read 200, the pressure of this gas should be 200. Now, this one is gauge pressure. So the absolute pressure of the gas inside is going to be 300 kilopascal. So this one is 300 kilopascal. Gauge pressure is 200 kilopascal. And atmospheric pressure is 100 kilopascal. Then how can we measure the pressure of this gas? We can use 2 devices. One to measure the gauge pressure, the other to measure atmospheric pressure. So what are the names? The one measures this gauge pressure is called manometer. The one measures this atmospheric pressure is called barometer. So we are going to study how manometer works and how barometer works, okay? This one is a typical manometer. This U-shaped tube is manometer. So what happened is that we have a gas inside the chamber. If this is an unknown gas, so we have no idea about the gas, and we install a manometer. This is a pressure measuring device, and filled with a fluid, usually liquid, whose density is known. So if you know the density of this liquid, you can measure the gauge pressure of this gas. And let's see how it works, okay? So in this manometer, do we know any pressure value in this manometer? One thing for sure is that this end is open to the atmosphere. So we can assume that at this interface, on this surface, the pressure is going to be atmospheric pressure. Yeah, this one is a surface open to the atmosphere. So you see this one is open. That means that the pressure at this surface is going to be the atmospheric pressure. Why is that? If you look at this one here, so we have this tube and liquid is filled up to here, then what happens? There is pressure by this liquid onto this interface in this direction. So this is the pressure by the liquid inside. And what else? There's a pressure by atmosphere. PATM. If liquid pressure is greater than air pressure, what happens? Yeah, the interface moves upward until you have the pressures are equal. If the gas pressure, air pressure greater than liquid pressure, moves downward. And if you see it, the interface does not move, that means that there's a pressure equilibrium, which means that ATM pressure and liquid pressure, they are the same. So if you see on the end of this manometer, if the surface does not move, that's our assumption, is that the pressure of this known liquid at this location is atmospheric pressure, which is PATM. So at this location, it is PATM. And then you can see the liquid is filled up to here at point 1, and there's a gas. So this is the interface. Number 1 is the interface between gas and this liquid. We usually use mercury here, Hg, from the manometer. I will explain, the why later when we talk about barometer. We use mercury here. So at this interface, what you see is that there's a gas pressure acting on here. There's a mercury pressure acting on here. Okay? Oh, you need to have a ruler or something, and you can. This should be an input. So assuming that we know H value, then you can calculate the pressure inside. Then, what is the equation that we know? Delta P is rho GH. Delta P is rho GH. Let's say that this one is, the interface between gas and the liquid is number 1. And we can make an imaginary interface at the same elevation in the same fluid at number 2. So this one is P1, this one is P2. Then can we use this delta P rho GH between PATM and P2? Yes, we can. By how? Between P2 and PATM, how do we determine delta P? Delta P is the difference in pressures. So between P2 and PATM, the difference in pressure is going to be P2 minus P80. So this one is P2 minus P80M. Can we say P80M minus P2? You can't, because P2 is greater than P80M. If you calculate P2 minus P80M, it's going to be a positive value. But if you calculate P80M minus P2, it's going to be a negative value. And delta P cannot be a negative value. So this is going to be rho density of mercury times gravity times H. So if you want to determine P2, it's going to be P80M plus density of mercury times gravity times H. So if you know the density, you determine P2. Then, what is the relation between P1 and P2? They should be the same. Because of this, because PA, PB, PC, PD, PE, they equal because they are in the same fluid at the same elevation. So P1 is the same as P2. So we can say P1 is the same as P2. Then that gives you the pressure value at this interface. So now let's talk about this gas. The pressure somewhere in this gas chamber, let's say this location. What is the relation between the pressure at this location and P1? P1 is greater than pressure at this location. But how much? Very small. By rho GH. What is the density of gas? It's usually negligible, very small, right? So the pressure change in this gas chamber is negligible, right? If it is water, if this chamber is filled with liquid, then the pressure change is significant, like diving into a swimming pool. But if it is gas, it's not significant unless this chamber is as big as Mount Everest. So if you go to, what is the tallest building here on campus, the towers, right? If you go to the top floor, you feel that, the pressure, the decrease is too much, so I need an oxygen tank to breathe. No, you don't, right? You can breathe normally, right? Because the pressure change in the air is negligible because of the low density of air. So when we calculate the gas pressure, we don't expect any change or any variation. We assume that the pressure of the gas is constant. So if you calculate P1, this is the pressure of the gas, P gas. So the gas pressure can be determined by this equation. So if you know the density of mercury, what is the density of mercury, by the way? We studied specific gravity. Specific gravity of mercury is what? 13.6. So how this thing work? Specific gravity is the density of mercury divided by density of the known substance, which is water. This one is 1,000. So the density of mercury should be 13,600 kilogram per cubic meter. So this one goes in here. What is the gravity? 9.8 meter per second square. If you know height, you can measure that. Then you determine the gas pressure, assuming that you know atmospheric pressure. But in reality, you cannot know the atmospheric pressure by this manometer. Then you can subtract P80M from here. This one minus P80M. What is it? Absolute pressure minus P80M. It's going to be P gas, gauge pressure. So you can calculate gauge pressure by rho GH using manometer. Okay? Any question? So by using this, the process, you can determine gauge pressure by a manometer. Then, if you want to determine the absolute pressure, what we need to know, the atmospheric pressure. How can we determine this atmospheric pressure? By using barometer. So let me explain, how this barometer works. The mechanism of this barometer is pretty simple. So you can make your own barometer in your house. Then let me explain how. So let's use the most common fluids, which is what? Water, right? So if you use water to make a barometer, it's pretty simple. You need to have a water tank filled with water, and you are going to buy a tube, and you're going to position your tube inside this water tank. So inside the tube is going to be completely filled with water. Okay. Now you're going to rotate this one counterclockwise 90 degrees. Then what's going to happen is that you have this tube positioned in this way. Then initially, everywhere in the water tank and tube is going to be filled with water. Then now, if you move this tube upward, then what you're going to see is that the water level goes down slightly. And eventually, what's going to happen is that you will see this is your water tank, and you have this tube filled with water only up to a certain height. So this is what happens. And now let's just you need to wait until this water level stops somewhere. Then you can read this barometer. And let's see, how it works. So what kind of pressure is acting on here? Let's talk about this surface of this water. What is the pressure on this surface? Come again? And what is the pressure? Pressure. Yes, this is the atmospheric pressure. It's acting on this surface. So there's an atmospheric pressure, PATM. So the pressure value is going to be PATM. We don't know what it is. Then, this is the pressure by the air outside. If this pressure is this the only pressure acting on this water surface? If the air pressure is the only pressure acting on this water surface, what's going to happen is that this water surface is going to move quickly downward, because the only, the pressure is the air pressure. So the net force is this way. So the water level goes down quickly. But if it doesn't move, that means there's a water pressure acting on this inner face for the same amount. So there's a water pressure acting on here. If you compare this atmospheric pressure and the water pressure on this inner face, which one is greater than the other? Air pressure, water pressure, or they are the same? They should be the same. If air pressure greater than water pressure, this one moves downward, until they are equal. If water pressure greater than air pressure, this one moves upward until they are equal. If you wait until the inner face does not move, that means there's a pressure equilibrium. Water pressure is the same as air pressure. So now, if you look at this figure and tell me what is the pressure at this location, this imaginary, the inner face, what is the pressure here? the same, PATM. So the pressure at this location is PATM. Now let's assume that that you can measure the height of this one. How? There are many different ways to measure the height. So let's assume that you can measure this height, h. Then what is the pressure at this location? What is the pressure at this location? PATM? If the pressure at this location is PATM, this is PATM, this is PATM, it's going to violate delta P is rho g h, because there's a height difference. We know that we have the density of water, there's gravity. So if they are the same, this one doesn't work. So the pressure at this location shouldn't be the same as the pressure at the bottom. Then, is this pressure greater than PATM or less than PATM? Less. That's correct, because pressure goes up this way. Then, do you know what is the pressure at this location? What is the definition of pressure? Force by fluid. Now, that's mathematical. But in physics, force exerted by fluid is pressure, right? So if there's a pressure, there should be fluid, right? So on this inner face, there's a water. What's inside here? Air. So initially, I positioned this, the tube in this way, completely filled with water, and rotate it so the water fills, up to the end, and then move this, the tube slightly upward so we can have the space like that. Then what is here? I mean, what kind of fluid is there? We make a hole somewhere on the tip, and then let the air goes in. No, then what kind of fluid is there? Gas? What kind of gas? It was completely filled with water. If you keep moving, the tube upward, what's going to happen? The water, continue to follow at the end? No. Because of the gravity, water sits somewhere here. Then what fills this space? Nothing. So what is this one? Vacuum. Because unless you make a hole, air cannot go in. This is vacuum. So what is the pressure by vacuum? What is the pressure by vacuum? The definition of pressure is going to be pressure is force exerted by fluid. Then what is the pressure of vacuum? Nothing. So the pressure at this, in here is going to be 0, because there is no fluid that can, provide that force. So there is no source of pressure. So is it vacuum? Then pressure at this location is going to be what? P is 0. Now, can you apply delta P rho g h between here, atmospheric pressure, and here, vacuum? Yes. What is delta P? Between 0 and atmospheric pressure, which one is greater than the other? Very silly question. This one is greater than this one. So delta P should be PATM minus 0 is going to be rho of what? Water times gravity times height, h. So if you know the density of this liquid, if you know the gravity and height, can you measure the atmospheric pressure? Yes, we can. Since we don't know h, and we know what is going to be the atmospheric pressure in this in Mount Pleasant. So let's approximately, calculate the H if you make a barometer. So the atmospheric pressure is going to be 101.325 kilopascal. Then density of water is going to be 1,000 kilogram per cubic meters. Gravity is 9.8 meter per second square times H. But be careful, there's a kilo. We just applied the dimensional homogeneity in the previous slide, and we confirmed that kilogram per cubic meters, meter per second square meter is going to be Pascal, right? Here, this one is Pascal, not kilopascal. So be careful when you do the calculation here. So anyway, if you do the calculation, 101.325 divided by the density of water, 1,000. Now divide by the gravity, 9.8. What is the height of this barometer? It's going to be 10.34. So if you do the calculation, this H should be 10.34 meters. So if you build your own barometer, this tube should be this much tall. So can you make one? You can, but it's going to be too big, right? So what is a way to decrease this H? How can we decrease this H? Any suggestion? Or do we make, the 10 meter, 11 meter, the barometer? Come again? But still the tube should be, the longer than 10 meters. So how can we decrease this value? Yes. For what? What kind of fluid? Lighter fluid than water or heavier fluid than water? Yes. What is the heaviest fluid that we can find? Mercury. So if you use a mercury, what is the density of mercury? 13,600 kilogram per cubic meters. So let's recalculate this H if you use a mercury. (101.325) divided by 13,600 divided by 9.8. We get 0.76. So if you use a mercury instead of water, if you use a mercury, then height, H, is going to be what? 0.76 meters. So which is about this much. So if you use a mercury, you can make your own barometer and then, put it somewhere in your room so you can measure the atmospheric pressure every in the morning. So 0.76 meters. Then let's go to weather.com and check today's atmospheric pressure. So let's go to weather.com, and search for Mount Pleasant, Michigan. So where is pressure? Weather today in Mount Pleasant, Michigan. What is the pressure? 30.3 kilopascal. ATM, bar, what is the unit? Inches. Is inch an appropriate unit for pressure? No. Then why there's an inch? Because there is a barometer in weather.com, and then whoever the employee read it, the red H value, and this is the H value. So they measure the H of the barometer. It is 30.3 inches. Then going back here, so according to this calculation, the H, when the atmospheric pressure is 101.325, at the sea level, H should be 0.76. Then what is 30.3 inches in meter? One inch is 2.54 centimeters. So 30.3 times 2.54 and divided by 100 will give you in meters. So you get 0.77. So if you calculate H, 0.77 meters. This is the today's reading when you have a barometer. And when you compare to this reference value, 0.76, pressure is higher than usual. When pressure is higher than usual, is there going to be a raining? No, rain comes when pressure is lower than usual, so you will expect that outside is going to be sunny. Okay? So if you just say, the pressure is 30.3 inches, this is actually incorrect. In science, you have to say 30.3 inches when you use mercury in the barometer. So it's going to be 30.3 inch mercury. That should be, the more accurate, the expression. Okay? So that's how barometer works. Any question? If you don't, and let's solve a couple of problems about pressure. The first one is a manometer. Is a multi-fluid manometer. I don't know why they use a multi-fluid. Maybe, let us practice, the pressure relations. So let's solve this problem. The water in a tank is pressurized by air, and the pressure is measured by this multi-fluid. So we have a mercury here, oil here, and water here. And we want to determine the gauge pressure of air in the tank. And we know H1, H2, H3. We know the density values of water, oil, and mercury. So we are going to determine the gauge pressure. Why do we determine the gauge pressure? Because we cannot determine the absolute pressure unless we know the atmospheric pressure. So what can we do? Usually you start from a point whose pressure value is known. So which one? Of course, we do not know the pressure of the air, but we know this end is open to the atmosphere. So we can say there is upside down triangle, this location, the pressure value is going to be PATM. We don't know what is PATM, maybe 100, 101, or 99. We don't know. Let's just assume that it's going to be PATM. Then we have a mercury here. So let's say this one is PATM at this location, and let's say this one is P1. The pressure at this point is P1. Can you determine P1 by using delta P rho G H? Yes, we can. We can apply delta P is rho G H between PATM and P1. Between PATM and P1, we know P1 is greater than PATM because this is the gravity direction, right? So delta P is going to be P1 minus PATM is what? The density of this liquid, which is mercury, Hg, times gravity times height, h3. So in this way, we can determine P1. So if you move this PATM to the right-hand side, we know P1 is PATM plus density of mercury times gravity times H3. Then, from this P1, there's an interface between oil and mercury. I'm going to say this one is going to be P2. Then, what is the relation between P1 and P2? If you remember this figure between PA, PB, PC, PD, E, F, G, what are their pressure values? They're all same, right? Then what is the relation between P1 and P2? They are at the same elevation within the same fluid, mercury. So P1 should be the same as P2. Am I right? Yes. So from here, we can say P1 is the same as P2. Now, let's find another interface right here. However, we cannot directly calculate the pressure at this location, so I'm going to make another imaginary interface at this location. So that is going to be right here at the same elevation as this interface between oil and water. I'm going to call this one is P3. So can you determine P3 from P2? Yes, by applying delta P rho GH. So let's do that. Delta P rho GH. How do you determine delta P between P2 and P3? Between P2 and P3, which one is greater than the other? We know P2, right? So delta P should be P2 minus P3. You cannot say P3 minus P2. In that case, delta P is going to be a negative value. You can't do that. You cannot do that, right? So delta P is going to be P2 minus P3 is the density of what? What kind of fluid? Oil. Density of oil times gravity times H. Do we know H value between these two? Yes, H2. So H2. So if you rewrite this in terms of P3, P3 is P2 minus density of oil times gravity times H2. Oh, wait, we already found P2, so let's substitute this one into here. Then we can determine P3. P3 is PATM plus density of mercury times gravity times H3 minus the density of oil times gravity times H2. So that is P3. Now let's find the next pressure. From P3, we have an interface between oil and water. So I'm going to call it P4. So this one is P4. So what is the relation between P3 and P4? Yeah. What is the relation? They're the same, right? So this one is P4. Now, what? Oh, between P4, I can find another imaginary interface here. I'm going to call it, this one is, at this location, P5. What is the relation between P5 and P4? They're the same liquid water at the same elevation. So P5 and P4 should be the same. So this one is P5. Now, finally, the air pressure is going to be P6. We discussed that. Gas pressures do not change. We assume that it is constant because the change in pressure in in a gas is negligible because of their low density. So we assume that P6 represents air density, air pressure anywhere. Then what is the relation between P5 and P6? They are not the same. Can you determine P6? Yes, by using this delta P rho GH. So this time I'm going to apply this one more time. Between P5, P6, we know P5 is greater than P6. So delta P should be P5 minus P6, not P6 minus P5. So P5 minus P6 is rho GH, density of what? Water, H2O, times gravity times H. What kind of H? H1. Now let's rewrite this equation in terms of P5. So this one becomes P6 is going to be P5 minus density of water, gravity, H1. So the air pressure is going to be P5 minus rho GH. We cannot say that because we need to solve for this P5, but we already found P5, this one. So let's put this whole thing here. So P6 is this one, PATM plus density of mercury, gravity, H3 minus density of oil, gravity, H2 minus density of water, gravity, and H1. That is P6, which is air pressure. So that's how you determine air pressure. That's not the end. We don't know this atmospheric pressure. So let's get rid of this atmospheric pressure. How can we do that? We subtract PATM from each PATM. So minus PATM. What is P air minus PATM? P air, which is gauge pressure, is density of mercury and gravity H3 minus density of oil, gravity H2 minus density of water, gravity H1. What is the mercury density? Mercury density 13,600. Gravity 9.6. H3. Do I have it? 0.46. Density of oil 850. Gravity 9.8. H2.3. Water density 1000. Gravity 9.8. And H1.2. So you can determine the gauge pressure of the air. Any question? If I give you this problem in your exam 1, can you solve it? Not yet, but if you practice enough, you can, right? So imagine that you know what we studied in chapter 1. We studied the first law of thermodynamics, second law, what is system, what is surroundings, what is process, what is the state and property, etc. Is there anywhere that I can that make a problem for your first exam? Not much, right? But in pressure, yes. So reasonably speaking, if you expect any problem from chapter 1, what is the section that I'm going to create? Here. Pressure. Not this problem, but any problem related to pressure would be in your first exam. Because I'm not going to create a question like, what is the system? What is temperature? What is the first law? No, that's too ambiguous, right? So I want to make if I want to make a problem, it's going to be pressure. That motivates you to practice the problem after this class, right? No? So any other question about this one? Yeah. The problem Yeah. So you can apply delta P rho GH vertically, right? So if you move from one to the other, you need to make sure that they are in the same fluid at the same elevation. Right. So you only have two options, either going upward or downward in the same tube using delta P rho GH. If there's any more, there's no more, the points you can move up and down. Then you find another location, imaginary surface, that is connected in the same fluid at the same elevation. So it's going to be either this one. If you cannot make, if you cannot move in both ways, that means that you went too far. Go back and find another location, right? Usually the interface is going to be always, a point that you can think of, the interface. So P2, PATM, P2, P4, and P6. Then if you look at this P2, there's only one imaginary surface you can make, that is P1. You cannot make P3 because they are not in the same fluid, right? So you find an interface first. In this case, how many interfaces do you have? One between mercury and oil, one between oil and water, right? And the one between water and air. So you can only make one imaginary surface that is connected by mercury. You cannot make P3 here. So there are only two from here, these two. And what about here? You can make one P5, yes, because they are in the same fluid. You can make one P3, they are in the same fluid. So you can make P3, 4, and 5. So you cannot make, as many, points horizontally. You can only make one or two, whether they are in the same fluid or not. So you can see you cannot make any imaginary surface here because they are not equal to anywhere else, right? Any other question? No? Okay. The last problem, so if we solve the last problem, you can see we have a new homework is coming up. So if we solve this one today, we have 7 minutes, so we can do it. And our first homework assignment is going to be due by a week from today. So this one, a gas is contained in a vertical frictionless piston cylinder device. The piston has a mass of 4 kilograms, and the cross-sectional area is this much. And we have a spring which is compressed above the piston. And the atmospheric pressure is 95 kilopascal. We want to determine the pressure inside the cylinder. So the pressure inside the cylinder is unknown. What is the first assumption we need to make? Is the piston moving or not? If it is moving, can we solve it? No. If it is not moving, can you solve it? Yes. When the piston is not moving, what does it mean in terms of force? Net force is 0. Right? No? Okay. So think about that. This is the piston. What about net force is positive, like upward? What's going to happen? The piston moves upward. What about net force is downward? The piston moves downward. So if you assume that the piston does not move, what is the net force? 0. Right? Think about yourself. You're standing right here, and your friend is pushing you. Then what are you going to do? You're going this way because somebody is pushing you. Net force is this way. If nobody is pushing you, you can stand still because the net force is 0. So when the piston does not move, that means that the net force is 0. That's how you're going to determine the pressure inside this piston cylinder device. So I'm going to look at this piston. What kind of forces are acting on this piston? Of course, pressure by the fluid, the unknown pressure, the unknown P. What else? Anything? Any suggestion? What do we have? Yes. 60 newtons. Spring force. Yes. Spring force is compressed. So the direction is going to be downward. So there's a spring force this way. By how much? 60 Newton. Anything else? So there's only one pressure? Yes, what? Yes, the weight of the piston. This way. The weight of the piston. How do you determine? Mass? 4 kilogram? No, that's a mass. So what is force by mass? Yes, times gravity. What is it called? Weight. Weight is a force. Mass is different, right? Mass times gravity is weight. W. That is the downward. That's it, or anything else? So there's only one pressure acting on, right? There's no other pressure. There's atmospheric pressure. So there's atmospheric pressure in what direction? This way. So how much? 95 kilopascal. So let's do a force analysis on this. Let's do a force analysis. How can we do that? You need to assign a positive direction. Can be downward or positive, doesn't matter. So in this case, I'm going to say upward is a positive direction. Okay, that's my assumption. And let's calculate the sum of forces. And by the way, the sum of forces should be what? What is the net force? 0. If it is positive, this one goes up because this is the positive direction. If the net force is negative, this one goes downward, okay? So I'm going to start with this unknown pressure P. What is the direction? Positive or negative? P. Positive. So it's going to be P. What about atmospheric pressure? Negative. So minus P ATM. And weight. Negative, positive. Negative. So minus W. What about 60 Newton? Spring force. Negative. Minus 16 Newton. Should be 0. And here P ATM is going to be 95 kilopascal. And here weight is going to be 4 kilograms times gravity 9.8 meter per second square. So if you solve it, you get P. Am I right, or there's a mistake? When I say it like that, there's a mistake, right? The one mistake I made. We have 2 minutes, so one mistake I made. Huh? Yeah, P is the unknown that we want to calculate. So that's not a mistake. There's a mistake here. So we know P ATM, we know W, we know 60 Newton. So we can calculate P. Am I right, or there's a mistake? There's a mistake, right? So what mistake is it? Look at the unit. Yeah, PATM, kilopascal. What is it? Pressure. 60 Newton. Is it pressure? No, it's a force. The force is different from pressure. So how can you convert this pressure into a force? Pressure is force divided by area. So force is pressure times area. So you need to multiply by its cross-sectional area of this piston. And what is it? cross-sectional area, 35 centimeters square. Oh, of course, you don't want to use centimeters. 100 centimeters is 1 meter. So 10,000 centimeters square is 1 square meter. So it's going to be 0. How many zeros? 0035 meters square. 0.0035 meters square. So if you solve it, you determine the pressure inside this piston cylinder device. If you do 56.9 kilopascal. Any question? So this completes chapter 1, and if you go to Blackboard, you can see there's a homework 1, and it's going to be due by a week from today. So that will be, so today is Tuesday, so next Tuesday, right before this class. So it's going to be 2 p.m. next Tuesday. That's the due, okay? There's no hard copy. Please take a photo or make a PDF and upload on Blackboard. Any question? No? Then see you on Thursday.